So let's continue our morning session with on Zenoh. Let's try to get to some live demo and some presentation. How can build something, can go from the cloud to microcontrollers, and we can get a nice use case to do that. So Angelo at the beginning presented one of the big motivations of why Zenoh was born and where we are stemming from, that is also industrial IoT. So let's take the use case of a smart factory. Let's try to understand what are the challenges that are in a smart factory, and then we end up at the end of this session to build something really that can be applied to a smart factory scenario. So first of all, what is a smart factory? Here I'm just taking a definition from SAP that a smart factory is an interconnected network of machines, communication mechanism, and computing power. So it's kind of an abstract definition in this case, but we can see later how can really the differentiation point of a smart factories and why Zenoh can be helpful in these scenarios. So first of all, first thing that we can think of when we talk about smart factory is that we have got multiple machines that are interconnected, but they are interconnected for a reason. They need to operate. In order to interoperate, they need to share data. Data, therefore, is key in a smart factory. So you think about like robots, production lines, robots for warehouses, etc. Those kind of machines, they need to communicate in real time, for example, for coordination, for safety, but also for monitoring, for example, with a control room. At the same time, if you think about this as a smart factory, it's smart because you want to apply something more to just operation that can be done without being so smart, right? So you can get the data, you can do data analytics, you can introduce, for example, artificial intelligence, machine learning that all operate the data. So in this scenario, already been introduced at the beginning by both Angelo and Frederick. With Zenoh, we can operate really with data in motion, data rest. So we've got real-time operation, data in motion. That needs to be fast, is safety critical, needs to be delivered as soon as possible for making the robot not, for example, crash against the wall. But at the same time, you want to integrate geo-distributed storages for then be able to retrieve the data later on, for example, for predictive maintenance of your production line. And in order to bring all these things together, you need to think about that a smart factory, and it was very well highlighted also by Frederick in general about edge computing, that is very heterogeneous in terms of type of devices, type of networks that need to be integrated together and live together, right? Just not that integrated once, they stay there forever, but things evolve over time. And in a smart factory, this kind of devices can think as little, as tiny as sensor, right? That little but a bit bigger, that like a small robot, bigger robots, as for example, a data center that can be either local to the smart factory, but also remote to, for example, to a cloud, right? So we need to have this kind of integration with different locations, different systems, that everything needs to be harmonized together. And it's very important in these scenarios that the tiny world, really, the thing, the microcontroller, are well integrated as data center, right? So you might think that we've got the real-time world going on for the microcontrollers, but everything needs to be supervised somehow, right, via a control room from human operator, and some processing, some data analytics, etc., is done in a data center. And those two worlds need to coexist, live together in a good manner. That is, was said by Angelo at the beginning, it was a help for integrating everything. And as things become more and more complex, I mean, the hell becomes even worse, right? So that's a very important point that we can see later in the live demonstration how we integrate this. In addition, we've seen that there are many protocols that are around. Frederick highlighted more details on what we're going to be doing now. For example, DDS, PCUA, MQTT, for example, REST API, Profinet, and many others exist today. And depending on the smart factory, for example, the production line, whether it's a warehouse or something else, you might end up having different type of communication protocols that live together, but as overall, they all need to communicate at some point of time. In addition, you also have multiple network technology. That's very important. You might have Wi-Fi, you might have now the 5G is coming. You can still have some serial communication from some old machine or some machine that doesn't need, for example, more powerful communication, or a Bluetooth, Zigbee, etc., etc. So there is really a huge spectrum of technologies, communication protocol that can live together in a smart factory. How can we deal with all of that, and how can we empower data for being transmitted, stored, and retrieved at any point of time? And there is also an additional point that you've got different type of communication protocol networks, but at the end of the day, what matters really is what you can do with your system. So how to empower your application and how to empower your use case and your scenario. In order to do that, and that's why also Zenoh, I believe, really is a good fit for this, gives you all the freedom to talk as you want for your application use case. You prefer, for example, for some application peer-to-peer communication, for example, in a warehouse with a swarm of robots to do coordinated delivery. Why should they be constrained by the technology? So you should be able to talk in that way. At the same time, you should be able to interact, for example, with a control room that is supervising this swarm of robots in such a way you can enable, for example, some safety measure. But now, I think it's enough talking about general story and what are the problems that exist. Let's move to the fun part, and let's try to build a virtual fence for our smart factory. And we are going to build it live today with the integration of microcontrollers, robots, and the cloud. First of all, what is a virtual fence? Just to be everyone on the same page to understand what we want to build. A virtual fence is a virtual barrier, okay, that can be triggered, and whenever, for example, an obstacle or some foreign object enters a given area. So this can be done via multiple technology, via radar, via ultrasonic sensor, etc. But the main point is that when an alarm is triggered because of this virtual fence, some action needs to be taken, right? For example, a robot should stop because a human entered, like in a given area. And in order to do that, it's really important to have this kind of fusion to be able to get data from the microcontroller that are sensing them and to distributed data, for example, on the control room, plus, for example, to interact with the robot to issue some safety stop command. So what we are going to build today is this scenario. That's a very simplistic scenario in this slide, but we're going to build little by little. We have some virtual fence that is built on top of some microcontrollers. We're going to have some mobile robots that are connected to a router, a Zenoh router, and we also have some storage that is integrated in our Zenoh infrastructure. The storage can be used, for example, to retrieve historical data on the robot, but as well, for example, to potentially visualize at a later stage what happened on the system. In the same way, once we've got this robot and this virtual sensor, for example, connected to our Zenoh infrastructure, we can also able to remotely control these robots, and in case of an alarm is triggered by the virtual fence, those robots will stop. So I think that we can really start to see cool things. I would like to move to the next phase with how to virtual fence. I will leave the floor to my colleague, Carlos Guimarães.
Thank you, Luca. So yeah, so now we are going to start showing some of the things that is happening. So as it was already highlighted by Luca, Frederick, and then Angelo, merging or making use of all this data that is available in factories is very complex to integrate with current technologies. They are there, they have some limitations. So we are going to show how you can do it with Zenoh, starting with the microcontrollers. So here, we will show in a camera the setup that we have here, but starting on the slide. So we have two microcontrollers. They are connected to a set of sensors. On the left, we have a microcontroller, which is an ESP32 connected to an ultrasonic sensor that basically is going to tell us the distance from the object. And we're going to publish some data under this key expression that was explained by Angelo. And then we have another microcontroller that is subscribing for this same data. Okay. At the same time, we also have this kind of control room where we are going to show the plot of the data, so you can see what is being published. Okay, so everything is happening with Zenoh. So now, if I move here, yeah. So when we move, so as was mentioning already, so we are, for the microcontrollers, we are using the Zenoh Pico implementation, which is written in C. So Fredrik already mentioned that it supports Zephyr, but it also supports Arduino, Mbed, and ESP IDF, RTOS system, operating system. Okay. So when we have the camera here, okay, so here we have the ESP32 connected to this ultrasonic sensor. So this is going to be very easy for me because Zenoh already provides all the capabilities to be plug and play and for a streamlined usage of it. So in the end, I just need to plug things. So I start by plugging the ESP32 with the distance sensor. So we can just test. So if you can show the graphical interface with the GUI, we can see. So it's beeping. So the closer we get, the faster is the sampling frequency. So the faster is going to beep. It's just like in our parking sensor in cars. Okay. So in the meantime, I'm also going to plug another sensor, which is a light sensor, just for the sake of having more information being published. And then by the end, I'm going to plug basically our light sensor, which was on the slide on the right side. Basically, what is happening is when something is below a threshold that is configured, the light is going to blink red or blink green. Okay. And then afterwards, we are going to see how this information is going to be used. So if I just plug the other information is being published from the sensor, which basically is just setting the data. In the control room, we are subscribing to this data, and we can see that information is being sent. Okay. So as you can see, now he's already connected. He did the automated discovery. So basically, I was just doing resets. So he could retry on the Wi-Fi, and whenever it gets too close, the light blinks red. Okay, then we are going to use this with the robots and to implement these virtual fence. So passing now the token to Olivier.
Okay, so in the presentation, we did have a few slides with code in it just to show you that publishing and subscribing with Zenoh is very simple. A publisher or subscriber fits in one page of code. So we'll not go into details here, but here how simple it is to use Zenoh. And now we will see how we can deploy an infrastructure to route all those data in a wide network. So all those sensors that Carlos deployed here, they could run and communicate peer-to-peer. This has some benefits, but if the number of sensors or application publishing and subscribing to data grows to thousands of nodes, for example, PubSub implies a lot of discovery and also implies a larger state to maintain on each node to maintain the state of all those connections. So with a microcontroller like those, you may not be able to afford such state to maintain. So you want an entry point in your system to give connectivity to the small sensor to the rest of the system. So in this case, for example, so we have a tool that I will deactivate that allow to display the Zenoh infrastructure. So in this case, in fact, we have one Zenoh router display, running on my laptop, and all those sensors discover this router and connected to it. Okay, and if I display PubSub data, we can see that there is data flowing between those sensors. Okay. Now let's imagine we have a second factory somewhere, and we want to connect this second factory and access data from factory to another. So let's run a second router and connect it to the first one. And Zenoh will automatically discover the new topology and adapt to the new topology. And if now, instead of subscribing to the plot, assume we want to display the access the distance information from the second factory, then so I don't have so now I can still visualize the data from the second factory, but Zenoh automatically detects that there is in the second factory some subscriber for this data and routes this data from the first router to the second router here. Okay, so obviously when you start to have some infrastructure components like the Zenoh routers, the drawback compared to peer-to-peer communication is that it could be a single point of failure. But Zenoh routing is self-discovering and very adaptive to topology changes and to failures. So if you deploy your routers on your application so that there is always two potential between any 2 points on your system, if any of the infrastructure components fails, Zenoh will automatically detect this new topology and reroute using a new path from any publisher to any subscriber. Let's stop that maybe, and let's assume now that we also have a data center in some cloud somewhere, and we want to also deploy a router there so that we can access the data from our factories in a more, let's say, web manner. And so here it is. And now we have a new topology. Okay? Let's go back to the slides. So, as said, Zenoh supports peer-to-peer communication, support brokered communication, routed communication, also supports mesh of peers communication, where maybe all your peers want to communicate peer-to-peer, but they cannot directly speak with each other, typically because they use a short-range radio communication. And so Zenoh can combine all those kind of communications, and you can use the communication model that better fits for each part of your system. So now we spoke about data in motion. Let's speak a bit about data at rest. And let's start deploying some storages in our system. So let's assume, for example, we want to store the luminosity in the cloud so that it is accessible to everyone, and maybe we want to do some analytics there on the luminosity. And let's assume we want to keep the distance published by the first factory in the first factory. Maybe the reason is that we want to access this distance with low latency. Maybe the reason is because it's some sensible data and we don't want to put it in the cloud we don't control. Maybe because it's just too big to be sent to the cloud all the time. So basically, I will deploy a storage in the first factory, storing all the distance published by the first factory, a storage in the second factory for the distance of the second factory, and a storage in the cloud to store all the luminosity from all the factories. And you can see we can do that using those resource keys expressions that we have on this slide. So let's do this. So now that I deployed a storage in the cloud that stores the luminosity, the storage has to subscribe to luminosity to store it, and suddenly Zenoh starts routing the luminosity up to the cloud. Okay. Now let's see how we can get this data. Now that we have stored different pieces of data in different places in our system, the problem is if I want to access, let's say, all the distance and luminosity from all my factories, I need to go fetch data, part of the data from the cloud, part of the data from each factory. Maybe those storages use different technologies. This starts to be very complex. So what Zenoh can do, and I can turn this to show, instead of the pub sub data, let's display the queries. So there is no query happening now, but let's assume that from the second factory, I want to access all the distances and luminosity. So you can see in small here that I got the last luminosity from the cloud on the last distance from the first factory. And if I run it again and you are careful of what happens in the graph, you can see that a client quickly appears connected to the second factory, but more importantly, Zenoh routes the query to any place that may have some data matching this query, and then will retrieve back all the replies to you. So you can, in a very simple way, query some data to a lot of different places in your system stored by different storages of different technologies. Okay? So this is a piece of code showing you again how simple it is to perform such a query. Note that Zenoh does not implement storages itself, but in fact has a plugin system that can be plugged into each router and that can connect to external storage technologies like InfluxDB, RocksDB, or MariaDB. Zenoh plugins can also connect Zenoh to other, let's say, middleware or protocols like REST, for example. So every router by default embeds a REST plugin that allows you to access your data through a REST API. So, for example, now that I have a router in the cloud, I can, using my favorite browser, I should be able to do, yeah. So I just ask for any data in the system, and I get the last distance and the last luminosity. It is as simple as that. So that's it for storages, but also note that then also bridge data from DDS. And now we will bring some robots into the demo. So maybe guys, if you can start the robot number 1. Yeah, this one. Yeah. So robots, a lot of robots, they come with what is called ROS2, which is a robot operating system that use DDS to communicate between the different parts. No, only one, please, guys. Only the first one, because. And so here maybe I should show the camera. So this is the turtle bot. So it comes out of the box with ROS2 installed on it. And the only thing, the thing we can provide with Zenoh is a Zenoh bridge. So this is out of the box, and we just deployed on it a Zenoh bridge. And this Zenoh bridge will allow us to do a lot of things with this robot. So I should be able to see in the tool. We have this robot with ROS2 running on it, and just thanks to deploying a Zenoh bridge on it, Zenoh DDS bridge, I can, for example, access the LiDAR information. Okay. So yeah, I need to show this as well. Maybe it's smaller. And so yeah, Carlos brought some objects near to it, and we can see the object here. As we have REST also API, what am I able to do is through my mobile phone to access, I don't know if you can see. So I can plot the data from the robot, and I can also drive it. Sorry, I got close to the fence. So yeah, so now just by deploying a simple Zenoh bridge on the robot, I can suddenly display the LiDAR, drive it from a mobile phone. This gives me a lot of possibilities. So yeah, now Carlos will show you how to integrate this robot with what we have done so far.
Yep. So basically now we have there another microcontroller, right closer, which basically has accelerometer and a gyroscope. So what's happening is whenever you tilt the command, the sensor, it will move the robot. Okay, if you can just take this. So as you can see here, I move it and he will control the robot. So what happens now is if we get closer to the fence, he will basically block the operation of the robot. So now I try to move it and it stops. So this is the goal of having this virtual fence. So that we can integrate and do the sensor fusion of all these sensors that we have in the factory, integrate them with the control of other operational processes that we also have in the factory, and be able to have a more fine control of what happens. So in this case, whenever something is too close, we block the operation of the robot. If the sensor is green, so meaning that there is no object in the range, the robot can move freely. So if we see it now, this one, so he's far away from the fence, so we can move it again. So if you go close again, yeah, sensor turns red and it stops.
Thank you. And now I will let the stage to Julia.
In the what was being deployed in the robot, which is running the standard ROS2, including DDS powered by Eclipse Cyclone DDS, is also the Zenoh Bridge DDS tool that allows to bridge DDS communication to Zenoh, and which then is connected to all the Zenoh infrastructure. So the LiDAR is data is subscribed by the LiDAR plotting, and of course there is also remote tele-op from the web application that Olivier just shown. And you can see also at the same URL, http demo.zenoh.io without the port number, you can see the acceleration data that is available in live. So you can go, I just post the link in the chat of the summit. So now let's bring another second robot in the dance. And what can we do with this? What we would like to do is, for instance, you have two factories, one with the robot you're driving and supervising, and you want to record everything that has been done on one robot, and to replay all your commands from for the first robot to a second robot. So what do we need for this? Mainly, as we've seen, all the commands sent to the robot are going through Zenoh. They are just publication on one topic, which is bot1/rt/tmdevel. So what we need is to store all those commands, and we will store those in the cloud, and to have another application later on to get all the commands that have been published, to get the history of the commands, and to republish to a second pass for bot2 up to the second robot. So what we will need for this is really to deploy a first storage in the cloud, which is a time series database. And for this, we will use InfluxDB that allows to store the history of the data that have been published by the command. And then later on, we'll have a ROS2 replay tool that for which we developed using Zenoh that will just get everything that have been published in InfluxDB and replay the publication on a different path, but with the same timescale. So let's do this. So first, I need to connect in the cloud. Thank you. Okay, so first step is to start a Docker container with InfluxDB. So InfluxDB will be running in a Docker container in the cloud. And now I will just instruct the Zenoh router in the cloud to load a specific plugin library to drive InfluxDB, to manage InfluxDB, and to create a storage on InfluxDB that will store all the command made on the robot. So now the storage is running and is subscribing to the command I made to the first robot. Again, no, let's replay. We are. And so what we just saw is really the ROS2 replay tool that has been fetching all the data, historic data coming from InfluxDB and replaying the data to the second bot, which is here. So now I leave the floor to Luca again for some takeaways.
Thanks, Julian, Olivier, and Carlos for a very nice live demonstration of the key capabilities of Zenoh, and specifically in the use case of our smart factory and the virtual fence. So, summarizing what we've seen so far, right? We've seen a few things, especially with the latest things shown by Julian about how can we use really Zenoh for dealing with data motion, data rest, that for real-time data, for example, controlling a robot from the smartphone or for the remote controller, but then being capable also to deal with the stored data that where the motions and the commands sent to the robot to replay to the second robot. It's easy to extend this kind of things, what you've seen. If you want to bring in, for example, digital twin, how you can have a digital copy and to replicate commands to the physical one, or the other way around. Or, for example, having coordinated movement of multiple robots, right? And you also seen how it's easy to do with Zenoh is to integrate different type of devices and networks from the microcontrollers, from Wi-Fi, and, for example, integrating with a storage and a router on the cloud, so going over the internet. And also how easy it is to do with Zenoh to integrate with third-party technology, like, for example, DDS. And as a consequence of being able to seamlessly integrate with DDS, we're able to really being able to interoperate out of the box with ROS2 robots. This brings us also to how not only Zenoh in the smart factory, but also Zenoh with the robotics in general. And we have seen that, again, this out-of-the-box integration with the ROS2 robots, that ROS2 is a very widely available framework for robotics development. And in addition to that, how Zenoh positions for robotics, for example, how can you use Zenoh? So we have seen so far Zenoh for inter-robot or robot to sensor or robot to cloud communication, but just also for as a reminder, and also as highlighted in the initial presentation by Angelo, in Zenoh we can also do zero copy. That means that you can use the Zenoh also internal to the robot or to any device to do very low latency and zero copy communication from multiple components of your application. We've also seen that Zenoh can really deliver high throughput. We've seen some slides. More information is also on our website in the blog. The links will come later at the end of this presentation. And also how Zenoh can provide a low wire overhead and a simple API. Also seen unexpected side effect of Zenoh being really low power and wire efficient, and to drain so low energy that we got also the power bank. Think about that our microcontroller was off, so he decided to shut down himself. So we stayed without our sensor. So this is really to sum up Zenoh. Again, we have seen a use case for virtual fence, a smart factory, but this can be extended to any use case for edge computing, really. So we've seen a live demonstration, but we really deal with the data in motion, data in use, data at rest, and it could be any data. Today we've seen smart factory, but it could be robotics, vehicles, IoT. It could be also, for example, a chat or a stream service. We can do that embedded microcontrollers up to the data center and the cloud, and we are also able to do work on top of the network technology and topologies. It does that by looking for some code snippet and location transparent API. So you care about data, so what you're interested in, what makes most sense of your application, without dealing about really when writing your application logic about all the underlying details for the deployment. And it's also can provide this pub/sub and distributed queries across this heterogeneous system. All of this really can facilitate when writing your system, your application, transcoding, geo-distributed storage, distributed control, decentralized, in a very plug-and-play fashion as we've seen today, that you can start adding more and more things to your system without the need to tear down or to reboot everything every time. With this, we conclude this session about the live demonstration. I will leave the floor to my colleague Julien Loudet for a teaser on Zenoh Flow.
Thank you, Luca. So, as Luca mentioned, to close this session about Zenoh and the live demonstration, we want to give you a small teaser into what we've been working on for the past year, called Zenoh Flow. So Zenoh Flow is a data flow programming framework for the cloud to thing. So before I move on to this presentation, with this small presentation, so what is data flow exactly? So data flow is the ability to decompose a complex application into small units, each that can be run in parallel independently, and to describe with a directed graph the flow of the data. So why is data flow important? Why do we use it? So with complex applications such as autonomous vehicles and robotics, we see that there is a need to describe how components are connected. And so after all that we have presented, what better way than to use Zenoh to do these connections? So our motivation is Zenoh, and especially the promise it holds. So becoming the backbone of many new distributed applications. And so Zenoh Flow builds on top of that. And our objective is to provide a cloud-to-thing framework that is the making of these complex applications. So what are our ambitions with this? Similar to Zenoh is to provide simpler and resilient foundations. So this data flow graph that is used nowadays for instance, autonomous vehicles is usually implicit, as in developers start their nodes, publish on some topic, and then create other nodes, subscribe, and this matching is manually done. With Zenoh Flow, we want it to be declarative, as in you would describe in a contract how things are connected. It's automatically deployed in the sense that we want to provide a Zenoh Flow daemon on your device. You tell us what library to load, we load it for you, and using Zenoh, we create the connections, the topics for you to avoid, for instance, collisions, name collisions on topics. We want to keep being Rust-based. So Rust brings many benefits to the table. So memory safety, concurrent safety, we want to keep that. And then we want to have a unified abstraction. So as we saw, Zenoh works on the cloud and in the things. So why not keep this same abstraction and capabilities everywhere? So what does it look like for now? So on the left you have a data flow description. For now, it's YAML, but this is the contract. This is how you tell us how your application is composed. Then we have ZFCTL. So it's our command line tool. With this, you interact with Zenoh and, for instance, the storages to do queries. And these, through Zenoh, interact with the daemon. So you have your computer, you interact with the daemon, and you tell it, OK, deploy my contract. I will not go into much detail. I just want to show you an example that we've been working on. So this is Pilot. It's an autonomous driving platform. And they used for their development a data flow framework called AirDosh that we replaced with Zenoflow. And when we say that we want that Zenoflow to make things easier, so we asked one of our colleagues to replace AirDosh with Zenoflow and to see if we can achieve it easily. The result is this. So skip the many terminals that are open. So this is the Carla simulator that simulates autonomous driving. And so this is what we've achieved after a few months, just simply porting Zenoflow, Pilot to Zenoflow. So we can see one scenario of the Carla challenges where the idea is to avoid collisions with the car. And what we can say about this, first, it's working. And the second thing is, right now the performances, thanks to Zenoh, are already better than AirDosh. We have numbers, but as we're in the process of writing a publication, we will not show them today. And what also we have is, thanks to Zenoh, we're able to port these many components not only on one device, but on many devices. So for instance, you could have part of your logic running on the cloud or on the edge. The sensors are in the car. Everything would be done automatically thanks to Zenoh and Zenoflow. As a final note, if you want to have more information about Zenoh and Zenoflow, don't forget to visit the website and the blog.